Hello, welcome to Principles of Energy Module 2. We're going to be talking about Newton's laws of motion. So this is our part 2 to that. I'm going to begin sharing. And here we go. So Newton's laws of motion, we're going to go through the three basic laws of motion. And so we have our law of inertia, force equals mass times acceleration, and the action-reaction. Sir Isaac Newton was a great scientific mind in the 1600s into the 1700s, and he also lived a very long life, and he influenced a great deal of physics and our understanding of the world. The laws of motion are something that are universal, therefore I can base them on anything and measure accordingly to them. And so without further ado, the first law, every object in a state of uniform motion will remain in a state of motion unless an external force is applied to it. Second law, force equals the mass times acceleration. So when we talk about external forces applying to something, we need to then have the way that we're going to figure out that force, and that's what the second law provides. And then the third law provides an understanding of how we react with these forces. And so every action has an equal and opposite reaction. We have different ways that we will say the first law, and so you'll hear that an object in motion will stay in motion unless acted on by an outside force. Another way that you can look at it is an object at rest will stay at rest, and an object in motion will stay in motion at constant velocity unless acted upon by an unbalanced force. The first law is known as the law of inertia. Inertia is the tendency of an object to resist change in its velocity, whether in motion or motionless. So if I had something that was on top of something else, so like I'm grabbing random objects, I've got my scissors on my board, right? Right now, my object is at rest, and it will tend to stay at rest. And there is forces acting on it. One of them is gravity, and it has a consistent mass. Therefore, it has a resistance to motion. And if I change the slope, eventually I will hit a point where the mass of the object will be overcome by the force of gravity, making it slide down the slope. Doesn't matter how massive the object is, eventually I will hit a point on my inclined plane, my simple machine, the inclined plane, right? Eventually I will hit a point where that mass will succumb to the force of gravity. And then, of course, understanding the laws of inertia, you can always do that wonderful magic trick where you pull the tablecloth and all the stuff on top of the tablecloth will stay in place. This only works if the tablecloth doesn't have a seam and you pull as evenly along. And actually, some people say you got to pull more like 90 degrees down off the table, and everything on the table will just stay right there. They might spin a little because there was a little bit of force given to it, but it resisted that force, and therefore the dish in the cup will stay right at the table. So, according to the first law, once airborne, unless acted on by an unbalanced force, it would never stop. And this is Newton's cradle, which is a great example of this first law in action, as well as the third law in action. So this creates the question, why then do we observe everyday objects in motion slow down and become motionless, seemingly without an outside force? Well, because there are things around us that cause resistance, right? So there's resistant forces. We might have greater mass, so we can move through those resistant forces, but there's still resistant forces. One of those resistant forces is friction. Friction allows for an energy transfer to occur. So when you think about rubbing your hands together, I'm creating friction my energy transference of creating this kinetic motion is thermal energy. So I'm creating heat, right, within that resistance. And there's 4 main categories of friction resistance. So the first one is sliding friction. You can think of ice skating. Rolling friction, you can think of bowling. Fluid friction, which is an air or a liquid that can create a resistance. And then static friction, which is an initial friction when you go to move an object that has been in place for a while. Just kind of a funny, it's true. It's true. That's why we wear seatbelts. We wear seatbelts because of Newton's first law. Which brings us to the second law. Force is equal to the mass times the acceleration. In order to create a measure of how forces are going to act upon one another, we have to actually figure out what is force. And so by this definition, force is the relationship between an object's mass and its acceleration. So heavier objects with more mass can be given the same amount of acceleration, but how that's going to react, the object that it's reacting on or acting upon, will be dependent on all the things within the relationship. By altering something's mass or altering something's acceleration, I'm going to change the force. So when mass is in kilograms, acceleration is in meters second squared. One of the things to keep in mind is that these things together make a unit of energy or force, not energy, I'm sorry, misspeaking, a unit of force known as a Newton. So if I am given a math problem that it is not in kilograms, or it is not in meters per second squared, I'm going to want to change the units of those before I find the Newton. And this brings me to one of the most important things that is going to take place in this course, which is paying attention to units. Paying attention to units will be so important to what you're going to need to do to this class. A lot of just job requirement in general is making sure that you're working in the appropriate unit of something. So how much force is needed to accelerate a 1,400 kilogram car 2 meters per second squared? To do that, I'm going to use my formula, and I can fill in the pieces. I have my mass. I'm going to fill in my acceleration, and then I can times my mass times my acceleration, the units of kilograms per meter per second squared will become the unit Newton. So we have units, making sure we're paying attention to units. And I know this is something everybody can look up, but it's also something that you have to spot the minute you see it. So just pay attention to everything that's taking place. The great mass, the harder they fall. This is because it's going to change the force on the item. So both of them have the same acceleration of 9.8 meters per second, but they have different masses, and therefore they're going to have a final force that is greater. So when something hits the ground, it will hit harder than the less massive item. This will be done through your coursework within the online coursework setup, but here's some basic check your understanding questions. If you want to work through them, they're right here. And the next slide is actually the answer key. So just making sure that you know what you're doing in this set. Which brings me to the third law. For every action, there is an equal and opposite reaction. This is best seen stepping off of a boat. If you've ever ridden in a boat and you go to step off of the boat and you kind of push your foot back, you create a force. And because there is less friction on the water than there is on like a car sitting on the ground, when you push back, you push the boat back at the same force with which you attempted to accelerate forward off of the boat. This has also been harnessed a great deal by nature. So another example in things that are man-made is rockets. When we launch a rocket, we're working with Newton's third law, and the force of acceleration on the ground has an equal and opposite reaction that pushes the rocket back up into the air. What the rocket is pushing off of is the exhaust force itself, not the ground. This is also a form of buoyant forces, so air-resistant particles that are overcoming gravity. A great example of Newton's law in nature is in fish. When you think of the fish, they push their fins back and the water propels them forward, equal and opposite reaction, right? So they're pushing back with their fins, and that creates the water force to push back at them equally and opposite, so it accelerates them forward. Another great example in nature is in bird flight. So when birds are flying, they push down with their wings, and the air pushes back on the bird at the same force that the bird wing pushed down, giving them lift as they're moving through. And this is just explanations as to how it works in more eloquent language than the simple way that I'm putting it. And so the last thing I want to leave you with is simple machines, just keeping in mind that simple machines all use Newton's 3 laws in their actions to help us do work. And so you have your inclined plane, your wedge, the screw, the lever, the pulley, and the wheel and axle. And then this is the example in the book. I like my picture better. So on that note, this concludes the concepts of Module 2 as you're working through the different questions. If you have any additional questions or want to bring anything up, please post in the discussion. That's the best place to do that as you're working through everything. And I hope everyone's having a great day. So I'm going to stop sharing, stop recording, and I'll see you in Module 3.